Welcome! In this video, I am going to be discussing the derivation of the solution to the logistic equation. The logistic equation is an equation describing basically the evolution of a population under some kind of restriction. It's usually discussed in Calculus 2, and the restriction itself could be anything from an environmental factor or just some kind of constraint that you have in your system. For example, if you're an animal population, you could have limited resources, and that could, of course, mean that you can only support a limited amount of individuals in your population. So the logistic equation, as we can see, is basically a first-order differential equation indicated from the order of the derivative here on the left. And it is nonlinear, as indicated if we expand the bracket in the y terms, we're going to get a terms of order of y squared. So that makes it nonlinear. The k value is a rate that is given in units of inverse time. It could be something like inverse years, inverse seconds, etc. And the m is the carrying capacity, which is again the limit that which your population can grow out to. Now, starting from first principles, again, this is how you'll see the equation written in a math textbook or an encyclopedia online. Well, my first move would be here to solve it, would be to pull out a negative, which will allow me to write this as y over m minus 1, and that's for me to not forget a negative sign later on in the derivation. Then from here, it's very easy to see the stuff that concerns the y right now is right there. So I can decide to just divide both sides here by that y stuff, so I can bring it all underneath the dy instead. On the right-hand side, I will keep all the time stuff, so the dt. And now to solve the separable equation, obviously what I need to do is integrate. However, this over here is not the derivative of some elementary function, so we have to think of a method to go about solving it. If you're thinking again, maybe partial fractions over here, if it smells like partial fractions, you're probably correct. So what I could do here is take care of breaking this fraction into a couple of partial fractions. I want this product to basically become a sum on the other side here. Again, I want these terms to be broken apart because I want you to see what the plan is. Because if I integrate those individually, they will yield logarithms. I know that. So I know I have to go in that direction. Now, based on partial fraction theory, again, the fact that this is linear, this y, makes us need only one constant above this fraction. The fact that the bracket here has a power of 1 doesn't mean we have any terms here of this sort of nature. We just have a single constant over here, c2, again, given by the fact that this is linear again, and the power of the bracket is 1. We only have a single constant c2, which is nice. The next step to solve this would be to multiply both sides by the denominator of the left-hand side. If I do that right now, you can clearly see what will happen on the left. We'll get cancellation of that term, but on the right, it might not be so obvious, so we'll open it up for you in another step over here. So we got the denominator of the left-hand side multiplying this term, and then multiplying this term over here. And there's a plus sign in the middle, of course. So we got a cancellation right now on the first term of y, and a cancellation of the entire bracket for the second term. That leaves me right now with 1 equals 2. And I'm just going to distribute the c1 in the bracket to skip another step here. I'm just going to already distribute it in. I'm going to have it written as c1y over m minus c1. And then over here, I'm just going to have, as you can see, plus c2 times y. That's all. Now over here, what I want to do in order to solve for c1 and c2, I would like to do a comparison between left-hand side and right-hand side. And to do that, I would like to write all sides in terms of orders of the variable y. I only have a 1 on the left-hand side, which can be thought of as multiplying y to the power of 0. I don't have any linear terms of y, so if I was to write out how many I have over here, it'd be 0 right now. Okay. The right-hand side, I can factor again over here, powers of y. So if I do so, I get c1 over m plus c2 times the first order y over here. And then I'm subtracting c1, which can be thought of as, again, multiplying y to the 0th power. Again, the reason I'm doing this is because I'm going to solve this equation through comparison, as you can see over here. So the factors that are multiplying the y to the first power are going to be set to be equal. That gives me right now c1 over m plus c2 is equal to 0. And the factors that are multiplying, again, the y to the 0 power will be also set equal. That means negative c1 will be set to 1, which makes c1 basically negative 1. Having the c1 right now, I can go ahead and plug it over here, which will give me negative 1 over m plus c2, as you can see over here. And that means right now that I will basically get that c2 is equal to 1 over m. That's about it. So having the constants right now readily available, I can actually carry out the original plan, which is to express the left-hand side as a sum. So I plug in c1, which was found to be negative 1, and I plug in c2, which was found to be 1 over m. This multiplication here can be thought of as being equivalent to having the m multiply the denominator right now, basically. And if I do that right now, what do I get? Well, the first term stays the same, but the second term here becomes 1 over, if I distribute the m, I have y minus m in this denominator. And look, I actually managed to open up this fraction as I desired, which means I can actually carry the integration forward from earlier. That's exactly what I'm going to do in the next step here. So I'm bringing back the integral, but I know right now that the left-hand side, this fraction here, can be substituted right now with this sum. That was the intention after all. So I'm essentially taking the integral of this entire thing right now. Of course, I can distribute integrals, right? Integration is a linear process. I can actually distribute the integration inside, which means right now I can have the dy in each of these fractions and integrate each of these fractions individually. So this is what I have left. Now, for this one over here, we can clearly see that this is the, again, derivative of a logarithm over here. So we write it as such. And then over here, this guy is also the derivative of another logarithm. Basically, the same idea carried forward. You can see if you differentiate this, for example, you just get 1 over y minus m, which is exactly what you have under the integral sign, which is nice. On the right-hand side, I don't have a t term, so I simply obtain a t term, and that's the result of my integration. However, remember that this is a linear differential equation, a first-order differential equation, which means it's going to have one constant on either side once we solve it without boundary conditions. So there's your plus c. I'm just choosing to write it on the right. Using logarithm rules over here, I can go ahead and combine the two logarithms as y minus m divided right now by y. Now the right-hand side basically stays the same. And my next move here is to raise everything to the power e. If you raise everything to the power e, the left-hand side is released, while the right-hand side looks like this. And since this is a sum of powers over here, I can write that e into two parts. One, again, being e to the c, and the other one here being e to the negative kt, as this gives me the same thing back. The reason why I'm choosing to do this right now is because I can express this gigantic constant here as another constant. In fact, I can even give it the same name without losing any generality. So having right now this written in this fashion, I proceed to solve. Again, I want to isolate for y as a function of t. So my next move here is to multiply both sides by y, giving me right now c times y e to the negative kt on the right-hand side. Then I will pull this term over here while I pull the m on the right-hand side. and I will factor the y on the left-hand side, giving me right now 1 minus c times e to the negative kt. And on the right-hand side, I am going to end up with just plus m. Now from here, I can simply just divide both sides by the factor that I've obtained on the left. And that leaves me with this answer, which is the general solution to the actual logistic differential equation. So I'm ready to go right now. This C is going to be determined given some kind of initial condition. This K is either given directly to you or given in terms of another population constraint. And this M is actually always given to you, pretty much. So, going now to our problem, again, we can see what we have in our hands. We have a model that's trying to describe the members of the Pacific halibut population in terms of kilograms, in terms of mass, as a function of time. And of course, it obeys the logistic equation, the model that we're trying to do. We've already solved the logistic equation, though. And the nice thing is they give us, again, the carrying capacity of the population in mass, as well as the rate, again, in terms of year units, per year units, I should say. So my first thing right now, before I even tend to question A, I want to see what those values do to my logistic equation. Or in fact, I should just say what they do right now to this answer that we've obtained here for the population. That's what I want to see right now. So what I'm going to do is I'm going to use first the initial condition, which is y of 0. I am saying that y of 0 right now is equal to 2 times to the 7 kilograms. But the right-hand side needs to also reflect this. So this side here, m has been given to me to be 8 times 10 to the 7 kilograms. Okay. And on the denominator, I have 1 minus c e to the negative k, which has also been given to me in terms of per year units. However, if I'm plugging in 0 for the time, this 0 right here will basically make the entire exponent here 0. And e to the 0 we very well know is equal to 1. Therefore, I just have 1 minus c in the denominator. So if I, again, over here, before I even move the 1 minus c, if I divide both sides by 2 times 10 to the 7, I obtain 1 on the left and basically 4 on the right. So right now, to solve for c, I just have to cross multiply here, move it on the other side. And I have free access right now to what c is, which is nothing more than negative 3. Right now, this has allowed me to write my actual logistic equation as 8 times 10 to the 7 for the carrying capacity. And then on the denominator, 1 minus minus 3 for the constant, which gives you a glorified plus here, 3, times e to the negative rate, which has been given as 0.71 per year, times time. And this is what I have in my hands, and I'm ready to make use of it in the rest of the question. So to do that, again, I want to answer part A, had me asked, what is the mass after 1 year? So over here, the reason why I've put 1 inside the argument for time is because the units that the k has been given is in terms of per year units. So in order to make the exponential unitless as it should be, I got to multiply here with units of years. So this is nothing more than a fancy plug and chug right now problem. So over here, if I want to solve for y of 1, I go ahead and plug 1 for the time in that exponential. That's going to give me e to the negative 0.71. If you carry out this actual calculation right now, what you're going to obtain is around 3.23 times 10 to the 7 kilograms. That will be the mass after a whole year. Now they could reverse the question and ask you something about when is the population going to achieve a certain mass. And that's exactly what they do in part B. They go, how long will it take for the mass to reach this amount? And what you have to do right now is reverse the logistic equation solution in terms of time. The first step that you got to do here would be probably to cross multiply this quantity across. So I'll have y times 1 plus 3 e to the negative 0.71t. And then on the right-hand side, I have the 8 times 10 to the 7 untouched. Then I distribute the y in here, giving me y plus 3 y e to the negative 0.71 times t. And then again, the right-hand side is completely untouched. Now again, I would probably move the y on the other side, and I will have the equation written like this. So 8 times 10 to the 7 minus y. And then I can divide both sides by 3y immediately, giving me this right now on the other side. At this stage, I probably want to take the logarithm of both sides, giving me on the left negative 0.71t, and on the right, the logarithm of the quantity that we had. All right. So at this stage, it's very easy to isolate for time. I just divide both sides by negative 0.71, which means, again, on the right, I'm going to have negative, the logarithm that you see here, basically, divided by 0.71. Okay, so that's how I isolate here for that time. And now if I want to find, again, what the actual time taken to reach this amount of mass is going to be, this is a glorified, again, plug and chug problem. So wherever you see y, again, you plug in the amount that you're looking for. So I have 8 times 10 to the 7 minus 4 times 10 to the 7 divided by 3 times 4 times 10 to the 7. And then you take the logarithm of this quantity and divide by 0.71. If you carry this out correctly, again, you're going to get a negative value from the logarithm, but you have that negative out here to cancel it. And then in the denominator, once you divide by 0.71, you're going to get about 1.55. 1.55 what? 1.55 years, if you remember, again, because of the way the rate was given to us. And this, again, over here concludes the example that I wanted to show you alongside the derivation. I hope you found this video helpful. If you did so, consider subscribing. Otherwise, thanks for watching.